What should be the next step in bridging the gap between natural and artificial intelligence? The solution is up for debate among scientists and experts. Yann LeCun, chief AI scientist at Meta and 2018 Turing Award winner, is banking on self-supervised learning, or machine learning models that can be taught without the need of human-labeled examples. For years, LeCun has been thinking about and discussing self-supervised and unsupervised learning. However, as his research in the disciplines of AI and neuroscience advanced, his vision converged on numerous interesting concepts and trends. LeCun recently spoke at a Meta event, formerly known as Facebook AI, on probable routes toward human-level AI, remaining difficulties, and the effect of AI developments. Welcome to today's episode of AI News. In this episode, I will show you the human-level artificial intelligence Meta is working on and what it could very soon look like. Deep learning's acknowledged limitations include the necessity for enormous training data and a lack of resilience in coping with novel circumstances. The latter is known as out-of-distribution generalization, or edge case sensitivity. These are the kinds of challenges that people and animals learn to solve from a young age. You don't have to drive over a cliff to know your automobile will crash. You're aware that when one thing obscures another, the latter exists even if it can't be seen. You are aware that if you hit a ball with a club, it will fly in the direction of the swing. The majority of these things we learn without being expressly educated, merely by observation and action in the environment. During the first few months of our existence, we form a world model, and learn about gravity, dimensions, physical attributes, causation, and other concepts. This approach assists us in developing common sense and making accurate predictions about what will happen in the world around us. We then utilize these fundamental building pieces to construct more complicated knowledge. Current AI systems lack this common sense understanding, which explains why they are data hungry, require labeled examples, and are extremely inflexible and sensitive to out-of-distribution data. The issue LeCun is attempting to answer is, how can we enable robots to acquire world models primarily by observation and amass the tremendous information that newborns accumulate just through observation? Deep learning and artificial neural networks, according to LeCun, will play a significant role in the future of AI. More precisely, he pushes for self-supervised learning, a form of machine learning that decreases the need for human input and direction in neural network training. Supervised learning, in which models are trained using labeled instances, is the more prominent branch of ML. While supervised learning has shown to be quite effective in a variety of applications, its reliance on annotation by an outside actor, mainly humans, has proven to be a bottleneck. To begin, labeling training examples in supervised ML models necessitates a significant amount of human labor. Second, supervised ML models cannot progress on their own since they require outside assistance to annotate fresh training instances. Self-supervised ML models, on the other hand, learn by observing the world, recognizing patterns, generating predictions, and occasionally acting and intervening, and updating their knowledge depending on how their predictions match the results they observe in the world. It functions similarly to a supervised learning system that conducts its own data annotation. The self-supervised learning paradigm is far more in touch with how people and animals learn. We humans conduct a lot of supervised learning, but the majority of our fundamental and common sense abilities are acquired through self-guided learning. Because only a tiny portion of the data available is labeled, self-supervised learning is a highly sought-after objective in the ML field. The ability to train ML models on massive amounts of unlabeled data has several uses. Self-supervised learning has made its way into numerous fields of machine learning in recent years, including big language models. Essentially, a self-supervised language model is trained by being given text snippets with certain words deleted. The model must attempt to forecast the missing components. Because the missing bits are included in the original text, this approach requires no manual labeling and may scale to very large corpora of text, such as Wikipedia and news websites. The trained model will learn accurate representations of text structure. It may be used for activities like text production or fine-tuned for later jobs like question answering. Self-supervised learning has also been used to computer vision applications such as medical imaging by researchers. In this example, the process is known as contrastive learning, and it involves training a neural network to construct latent representations of unlabeled pictures. For example, during training, the model is given several copies of a picture with varying alterations, e.g., rotation, crops, zoom, color modifications, different angles of the same object. The network's parameters are adjusted until the output is consistent across multiple versions of the same picture. The model may then be fine-tuned on a subsequent challenge that requires fewer tagged photos. Scientists have lately experimented with pure self-supervised learning on computer vision challenges. The model must anticipate the obscured areas of a picture or the next frame of a video in this example. According to LeCun, this is a really challenging task. Images are very three-dimensional spaces. Pixels in a picture can be organized in nearly endless ways. Humans and animals are skilled at anticipating what will happen in their environment, but they do not need to forecast the world at the pixel level. We employ high-level abstractions and prior information to intuitively filter the solution space and narrow it down to a few viable solutions. For example, when you view a video of a flying ball, you expect it to continue on its path in the following frames. You anticipate it to bounce back if there's a wall in front of it. You know this because you understand intuitive physics and how hard and soft bodies operate. Similarly, you would anticipate a person's facial characteristics to alter over frames when they are speaking to you. As they talk, their mouth, eyes, and brows will move, and they may tilt or nod their head slightly. But you don't anticipate their mouth and ears to move positions unexpectedly. This is due to the fact that you have high-level mental representations of faces and are familiar with the limits that control the human body. Self-supervised learning with these sorts of high-level abstractions, according to LeCun, will be critical to generating the kind of robust world models necessary for human-level AI. Joint Embedding Predictive Architecture is a key component of the solution LeCun is developing, JEPA. JEPA models develop high-level representations of dependencies between two data points, such as two video snippets that follow each other. JEPA substitutes contrastive learning with regularized approaches capable of extracting high-level latent features from input and discarding unnecessary data. This enables the model to draw conclusions from high-dimensional input, such as visual data. LeCun also discussed a modular architecture for human-level AI at the Meta AI event. This design will rely heavily on the world model. However, it will also need to communicate with other modules. A perception module, for example, receives and analyzes sensory input from the outside environment. Perceptions and predictions are transformed into actions by an actor module. A short-term memory module records actions and perceptions and fills in the model's knowledge gaps. A cost module aids in determining the intrinsic, or hardwired, costs of actions as well as the task-specific value of future states. Furthermore, there is a configurator module that adapts all other modules based on the precise duties that the AI system wants to do. The configurator is critical because it directs the model's limited attention and processing resources toward information relevant to its present activities and goals. For example, if you're participating in or watching a basketball game, your perception system will be focused on certain elements and components of the world, e.g., the ball, players, court limits, etc. As a result, your world model will attempt to anticipate hierarchical aspects more relevant to the job at hand while discarding irrelevant information, e.g., actions of spectators, the movements and sounds of objects outside the basketball court. LeCun believes that each of these modules may learn its duties in a distinct manner and interact with one another via high-level abstractions. This is similar to the brains of humans and animals, which have a modular architecture, different cortical areas, hypothalamus, basal ganglia, amygdala, brainstem, hippocampus, and so on, with each having connections with others and their own neural structure that gradually updates with the organism's experience. The majority of debates concerning human-level AI are upon computers that replace natural intellect and can execute every work that a person can. Naturally, these debates go toward issues like technological unemployment, singularity, runaway intelligence, and robot invasions. The future of artificial general intelligence is hotly debated among scientists. Will there be artificial intelligence without the urge to survive and reproduce, which has been the driving force behind the evolution of natural intelligence? Is consciousness required for AGI? Will AGI have its own desires and goals? Is it possible to build a brain in a vat without a physical shell? These are some of the philosophical concerns that remain unanswered while scientists make incremental progress toward the long-desired goal of creating thinking robots. However, a more realistic research area is to develop AI that is compatible with human intellect. This, I believe, is the potential of LeCun's field of study. This is the type of AI that may not be able to create the next great innovation or write a riveting novel on its own, but it will undoubtedly help people become more creative and productive, as well as discover answers to complex issues. It will most likely make our roads safer, healthcare systems more efficient, weather forecast technologies more reliable, search results more relevant, robots less stupid, and virtual assistants more useful. In fact, when asked what he thought was the most exciting aspect of the future of human-level AI, LeCun said he thought it was the amplification of human intelligence, the fact that every human could do more stuff, be more productive, more creative, spend more time on fulfilling activities, which is the history of technological evolution. Meta isn't the only company working on creating a human-level artificial intelligence, since the monetary rewards of such a thing would be enormous. So, what is your opinion on the creation of human-level artificial intelligence? Do you believe that companies will succeed in doing so, and if they do, would this be a positive for humanity or a negative? Please tell us your opinion in the comment section below. I would love to hear what you have to say about it. Thank you for watching AI News. We consistently report on the newest technologies that are shaping the future of our world. We'd appreciate you subscribing and watching our other videos. See you around and take care.